Welcome to this lesson on the Carnot cycle. The Carnot cycle represents an ideal heat engine, a theoretical model that helps us understand the maximum efficiency possible when converting heat energy into useful work. This concept is fundamental in thermodynamics and sets the benchmark for all real-world engines. The Carnot cycle is a theoretical thermodynamic cycle that represents the most efficient possible heat engine operating between two temperature reservoirs. It was proposed by French physicist Sadi Carnot in 1824. This cycle is purely theoretical, meaning it cannot be built in reality, but it serves as an important reference point for understanding engine efficiency and the fundamental limits of energy conversion. The Carnot cycle consists of four distinct stages that the working substance undergoes. Stage 1 is isothermal expansion, where the gas expands at constant temperature. Stage 2 is adiabatic expansion, where the gas continues to expand without heat exchange. Stage 3 is isothermal compression, where the gas is compressed at constant temperature. And Stage 4 is adiabatic compression, where the gas is further compressed without heat exchange, returning to its initial state. In the first stage, isothermal expansion, the gas absorbs heat from the hot reservoir. As the gas receives this thermal energy, its volume increases while the pressure decreases. The key characteristic of this stage is that the temperature remains constant throughout the process, maintained at the hot reservoir temperature T, sub H. The gas performs work on the surroundings as it expands. The second stage is adiabatic expansion. Here, no heat is exchanged with the surroundings, meaning the system is thermally isolated. The gas continues to expand and perform work, but since no heat is being added, the temperature drops. The gas cools from the hot reservoir temperature T sub H down to the cold reservoir temperature T sub C during this expansion process. In the third stage, isothermal compression, the gas releases heat to the cold reservoir. During this process, the surroundings do work on the gas, causing its volume to decrease and pressure to increase. Similar to stage 1, the temperature remains constant throughout this compression. Staying at the cold reservoir temperature T sub C, the gas expels thermal energy as it is compressed. The fourth and final stage is adiabatic compression. Again, no heat is exchanged with the surroundings during this process. The gas continues to be compressed by work from the surroundings. Because the system is thermally isolated and work is being done on it, the temperature rises from the cold reservoir temperature T sub C back up to the hot reservoir temperature T sub H, returning the system to its initial state and completing the cycle. The Carnot cycle can be visualized on a pressure-volume diagram, or PV diagram. The cycle forms a closed loop with four distinct processes. Process 1 is the isothermal expansion, shown as a curve at high temperature. Process 2 is the adiabatic expansion, where the curve steepens as temperature drops. Process 3 is the isothermal compression at low temperature. And Process 4 is the adiabatic compression, bringing the system back to the starting point. The area enclosed by this loop represents the net work output of the engine. Now let's understand efficiency. Efficiency is a measure of how well an engine converts heat into useful work. It is defined as the ratio of work output to heat input. In other words, efficiency tells us what fraction of the absorbed heat energy is successfully converted into mechanical work, with the remainder being expelled as waste heat to the cold reservoir. The efficiency of a Carnot engine is given by a remarkably simple formula. Eta equals 1 minus T sub C divided by T sub H here. T sub H is the temperature of the hot reservoir, and T sub C is the temperature of the cold reservoir. Both temperatures must be measured in absolute units, such as Kelvin. This formula shows that efficiency depends only on the temperature difference between the two reservoirs. The greater the temperature difference, the higher the efficiency. The Carnot cycle is special because it sets the theoretical upper limit for engine efficiency. No real heat engine operating between the same two temperatures can exceed Carnot efficiency. This maximum efficiency is achieved because the Carnot cycle uses only reversible processes, meaning there are no energy losses due to friction, turbulence, or other irreversibilities. All real engines have lower efficiencies because they involve irreversible processes and energy losses. Let's review the key points. First, the Carnot cycle consists of 4 reversible processes, 2 isothermal and 2 adiabatic. Second, the efficiency depends only on the temperature difference between the hot and cold reservoirs. Third, the Carnot efficiency represents the maximum theoretical efficiency possible for any heat engine. And finally, all real engines have lower efficiency than the Carnot engine because they involve irreversible processes and energy losses. Understanding the Carnot cycle helps us appreciate the fundamental limitations and possibilities of thermal energy conversion.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.